Okay, so now it goes to the second and the third part of this lecture. We're trying to understand this generalization bound. We want to understand it more. With now this m factor go into the equation. So there are two specific things that we want to look at. One is the hypothesis set h. The other one would be the target function f. And then we also want to understand the upper and lower limits in this equation, which will become clear later on. So what is the learning goal of a learning algorithm? Well, the ultimate goal of learning is to ensure that your outsample error applied to your final hypothesis, which is the hypothesis that you're going to use for your deployment, is very, very small. Okay, so you care about the outsample error applied to G. You want it to be as small as possible. There are two ways to achieve this. Okay, the first one is to make sure that your outsample error is very, very similar to the in-sample error. Now how do we achieve that? Well, you need to use the Hoeffding inequality to achieve that. The second part of the equation is to ensure that E in, the in-sample error, is very close to 0. Okay, so that requires the training error to be very small. So now let's try to understand a little bit more about these two equations. Why do I mean that you want to have a Hoeffding inequality? And what do I mean that you need to have a training error to be small? Let's look at the first one, the Hoeffding inequality case. What is the outsample error? The outsample error is a deterministic quantity. And then what is the in-sample error? The in-sample error is the finite sample training error that you have seen during your training process. If you ever want to have your outsample error to be 0, to be close to 0, the first thing you want to make sure is that you want to make sure that your outsample error is close to your in-sample error. Now, why do you want to ensure that? Well, because if I can ever ensure that my in-sample error is close to 0, that is my training error is small enough, then having this first part of the equation, I will be able to claim that my outsample error is also close to 0. And Hoeffding inequality is really achieving this goal, because Hoeffding inequality says that give me enough n, then according to the equation, the probability of having E in very, very far away from E out will become smaller and smaller. So this is given by the Hoeffding inequality. Now the training error says that as long as I can make sure that I can fit well to my data set, then I can make my training error small. So you can see that these two are the goals of a learning algorithm. As long as I can make the Hoeffding inequality to hold, and as long as I can make my training error to be small, then according to this principle, my out-of-sample error should become small. So Hoeffding inequality holds where n is big, and training error is small when you train well. So now let's look at the case where your hypothesis set H is complex. Okay, so let's recall the Hoeffding inequality. The Hoeffding inequality says that the probability of having an in-sample error compared to the outsample error bigger than epsilon is upper bounded by 2m times my exponential function as a function of n. So this is the Hoeffding inequality applied to the final hypothesis. So if H is complex, then m would be a very, very big number. Okay? So think about if H is a complex hypothesis set, you have a lot of hypotheses to choose from. Think about a deep neural network compared to a linear classifier. And of course, a deep neural network is more complex. And you can hypothetically imagine that the number of hypotheses there would be more. Now, I'm just hand-waving and arguing that the n will be larger. We need to define it more carefully because both cases, they have infinitely many hypotheses. Okay, but you can sort of say that as H becomes more complex, then the number of hypotheses should in principle becomes more. And therefore, what will happen? Well, if you look at this equation, when n becomes big, then the right-hand side of this equation becomes more and more loose. And therefore, the approximation by the Hoeffding inequality will become worse and worse. So you are not able to bound the Hoeffding inequality. But if H is complex, you will have more options during training. Now that can be understood because if you have 10,000 data points, but then you have extremely complicated deep neural network, and of course you can fit better to this training set than if you're using a very small network. Okay, and therefore if your H is complex, and so you have more options to use during training, then training error should in principle be improved. And therefore, what will happen to this paired equation is the following. You have the E out, which is the testing error. You want it to be close to the training error. That is unfortunately not happening because your hypothesis set becomes more and more complicated. The good news is that because your hypothesis set becomes more and more complicated, you will have more options, and therefore you should fit well in your training, and therefore your E should approach to 0. So that gives you some notion of trade-off between the Hoeffding inequality and also the training error. In this case, you can see that the training error can go down. However, the approximation error will go up. There is no free lunch here, as we are showing. That as long as you make the hypothesis set complicated, you need to trade off between these two. Okay, so that means what you can do is that you should actually try to choose a model that is good enough that it can approximate the in-sample error. Okay, so you want to choose a model that is complicated enough that you can make this E in as small as possible, but not too complicated, because if it is too complicated, then you will actually make this approximation worse. And therefore, when you choose a model, the complexity of the model has to be carefully adjusted. So that also goes into the question of why simple model usually is better. It's because when you have a simple model, while you are not able to make this in-sample error to a very small number, this out-sample error, you can now make this approximation very, very well. Now let's talk about the other case when you have a complicated target function. So in this case, let's try to recall the Hoeffding inequality again. So the good news is that the Hoeffding inequality is not affected by your target function f. So you can choose whatever target function here. And since my right-hand side of the Hoeffding inequality doesn't depend on f, you can apply the Hoeffding inequality. So even if the function f is extremely complex, Hoeffding inequality remains true. So that's the good case. But the bad news is that if your target function is very, very complex, that will be very difficult to train. And so what will happen is that in the set of equations, so you have these two equations, your E out will become the same as before. Okay, by having a more complicated f, you are not going to make the Hoeffding approximation worse or better. It will just be remaining the same. However, what will happen in this set of equation is that your in-sample error will become big. Now, why is this the case? Your in-sample error says that I try to approximate all my sample data points, my training data points. But if my target function is very complicated, it's no longer a strict line, but it's a complicated high-order polynomial, and that is how I draw the samples from. If that is the case, then your in-sample error has to be big because it will be extremely hard to fit all these data points because the data points, they actually come from a very complex data set. So in this case, you have another trade-off here, where your target function is not changing the Hoeffding approximation, but it makes your training very, very difficult. So the conclusion here is that when in the previous slide, when you remember that when we have a complex h, there is a trade-off associated with the approximation. But now when you have a complex target function, the error will go to your training error. So you can make your h to counter h, but the complex h will make the Hoeffding inequality worse. Okay. So what this says is that now, of course, you can say that, hey, my f is really complex, and therefore what can I do is that I want to increase the complexity of my h. Now, if you do that, then you can make this in sample error to be smaller. But then, as we showed before, then your Hoeffding approximation become worse. Okay, so now we have talked about the relationship between your hypothesis set and also your target function. Let's spend some time trying to rewrite this Hoeffding inequality into a form that we can draw some additional insights from. So recall that the Hoeffding inequality is written in this form. It is the probability of certain events that is upper bounded by something. So this is the same as if I'm just taking the complement and I write that the probability of the in-sample error compared to the out-sample error is at least the confidence level that I'm looking at here. It would be 1 minus delta. Now, equivalently, what we can say is the following. We can say that with probability 1 minus delta, that this out-sample error E out of G is upper bounded and lower bounded by 2 terms. Okay, so you have the lower bound, which is E in of G minus epsilon, and then the upper bound will be E in of G plus epsilon. So what this means, well, this actually comes from the equation here. This equation says that I have the confidence of having this probability event to hold with a probability of 1 minus delta, and the event to hold would just be the event that my absolute value of this E in and V out is bound between the epsilon. Okay, so now I want to spell out this equation here. Then you have E out is bound between E in minus epsilon and E in plus epsilon. In other words, I want to say how good is my E in compared to my E out, and since I want to measure my E out, I want to use my E in to measure my E out. I will just write down the sandwich inequality and say that my E out is upper bounded by E in plus something and is lower bounded by E in minus something. So what is the meaning of this delta? As we discussed before, this delta is actually the confidence level. And so you can equate this right-hand side, 2m e to the power minus 2 epsilon squared n equal to delta. And you can move around the equations, and you can show that the epsilon is actually given by this equation of the square root of all these things inside the square root. Now, when you try to plug this result into the previous equation, you can show that the E out is actually upper and lower bound by these epsilons. And what are the epsilons? You put it in, you can show that the E out is upper and lower bound by E in of G minus the square root, and then E in plus the square root. Okay, so now we want to look at these two equations. One is the lower end, the other one is the upper end. And so what will happen in the lower end is that you have this E out, you have this E in minus something, and on the other side you have E in plus something. These two have two different meanings, and let's look at them. Okay, and this pair of equation is called the generalization bound. It says that how well is my outsample error or my testing error related to my training error. Let's spend some time trying to interpret this generalization bound. In this generalization bound, I have E out that is lying between these two quantities. N is the number of training samples. And then, of course, in this equation, the more is the better. Now, why is this the case? You look at the equation here. You have N that's sitting in this square root thing. And so as n goes to infinity, then you can see that this entire term will go to 0, so is the other term. So when they go to 0, then E in will equal to E out. The delta is called the confidence level or the tolerance. Okay, so the delta is called the confidence. 1 minus delta is called confidence. So now if you make the delta extremely small, okay, then you are very conservative. So that means what? Well, if you make the delta small, you want this E out to be extremely close to your E in. You don't want to play any game. You just want to make sure that your E in is absolutely close to your E in. Then in that case, you are very conservative. You have a very small delta. In other words, that you need a very, very big n in order to compensate this log of 1 over delta. Now, what is the m? M is some kind of model complexity. It is measured in that way. If you have a large m, then you have a very complicated model, and so you need to have a very large n to compensate for the log of m. There are two sides of this generalization bound. There is an upper limit. There is also a lower limit. Let's talk about the upper limit first. The upper limit is given by this set of equations. You have E out is upper bound by E in plus all these equations. So what it says is that your E out cannot be worse than your E in plus certain epsilon. This is a performance guarantee, and that's the worst you will ever have. Now this performance guarantee is useful. It says that I'm going to run this algorithm, and I'm going to give you this hypothesis, and then I want to show that my testing error, my generalization error, my E out will not be worse than E in, my training error, plus some constant. Okay, and you will never be able to become worse than this quantity. And therefore, if the square root of if my epsilon that term, okay, if this term is very well controlled, then I can pretty much say that my outsample error will be close to an in-sample error. Okay, so that will give you the worst case guarantee. You won't be able to do worse than this. The lower limit is also very, very informative. The lower limit says that my E out will not be better than E in minus something. Okay, so you look at this equation. E in here, E in here you have to minus the E in. Okay, so this is a little bit lower than the E in value. Okay, and so that means the E out cannot be better than E in minus that epsilon. And that is the intrinsic limit of your data set, which controls the n. Okay, it says that once you give me the data sets, once you tell me the model, and then once you tell me the confidence level that you want to achieve, then there is a fundamental lower bound that you cannot do better. Okay, that's just the fundamental limit of your learning algorithm. That is the intrinsic limit of your problem. You will not be able to do a testing error that is lower than this lower limit. So the difference between the upper and the lower is the following. The upper gives you the worst case guarantee. You won't do worse than this upper limit. So that's like giving you the insurance. The lower limit is telling you what is the best you can ever achieve. You cannot go beyond that. And that is just the fundamental limit of this algorithm. There's no way that you can go better than this lower limit. Okay, so now we understand this generalization bound. We have two ways of interpreting this generalization bound. We can look at either using the Hoeffding inequality, using the probability setting, or we can turn it into this thing called a generalization bound, and then we try to understand it from the m, the n, and also the delta from this perspective.